I wanted to talk about the area between two curves. And I want to draw an old picture I've shared with you before because it relates greatly. So the picture that I'm talking about is, I can draw the following. So let me draw a little something like this. And then let me have a curve. And my curve, here's A and here's B. And so my curve looks like this. Okay. And I'm going to copy that picture. This is y is equal to f of x. And I'm going to copy that picture over. Let's copy that guy. Let's put it over here like this. And we know that if you wanted to find the signed area, the signed area is just the integral from a to b of this function f of x dx, right? And we also know that the area above the x-axis is positive, the area below the x-axis is negative, and then this third area here is positive. That's what we called signed area. So the other thing that we had was we had what we called total area. And the way you calculated total area was you had to integrate the absolute value of f of x. Now, what's the net effect of the absolute value? What the absolute value does is it takes that negative area that we just had there and it makes it positive, right? So I'm going to erase this negative part over here. And then I'm going to, maybe I'll switch colors to green, and then I'll just flip it like this. So that negative area became a positive area. So I guess the idea is that the total area is always going to be bigger than or equal to the signed area, because we are subtracting some positive number here, and over here we multiply that negative area by -1 to make it positive. Was there any questions about this scenario? Because I'm using this scenario to try to motivate area between two curves. Okay. We had something related, so I just want to remind you of the related thing. Maybe I'll do this in purple. We could talk about net displacement. And net displacement that occurs when you're not integrating just any function, you're integrating the velocity function, right? And the variable isn't x, it's t. So we had talked about that recently as well. And then we had talked about sort of total distance traveled. And that was very similar. You just find the absolute value of the velocity function. You integrate with respect to time. So I'm just trying to sum up what we had talked about earlier, and this was the scenario that we had. Okay. Now, what are we talking about now? What we're talking about is area between two curves. So if I want to talk about in section 5.1, talk about area between two curves. Really, we've actually done area between two curves over here before. Curve 1 was equal to y equal to f of x, and curve 2 was actually just the x-axis, right? So we can think of, instead of thinking of this as an area under the graph, we can think of it as the area between this blue function and just the x-axis. So our second curve, I'm going to say, is the x-axis. So the x-axis has an equation that's y is equal to 0, right? And what I want to do now is I want to be able to change what this second curve is. So instead of having it be the x-axis, I want it to be any curve. And what we see, when you looked at that video, what you saw was that to find the area between two curves, you could just integrate from A to B, whatever, one function minus the other function with respect to x. Now, when you do this integration, this function is the top function, and this function is the bottom function, right? And this actually completely matches what we had talked about earlier over here, because if you think of the second curve as the x-axis, you're just basically putting a 0 here. And when you put a 0 here, that just gives you the original area that we had. Okay. So why don't we take a look at our 5.1 worksheet? And you'll see I didn't refer to it as top bottom. I referred to it as bigger and smaller. There's a reason why I said bigger and smaller, but for now we can think of it as top and bottom. And what's really happening is, when we found the area before, we first found the area of rectangles, and the height of the rectangle was determined by the height of the function, right? But when we're talking about the area between two curves, the height of the rectangle doesn't go all the way down to the x-axis. The height is the length between your blue curve F and your green curve G here. So whatever this distance, that's going to be the height of your rectangle. So all we're doing is we're changing how we calculate the height of the rectangle. Okay. So if you looked at example 1, this was a simple example with 2 lines over here. When we want the height, we kind of are thinking of it as chopping it up. And then when you want the height of your rectangle, you just subtract the 2 y values, and that's a little bit of thickness. So that's that little bit of thickness that lies on the x-axis. Okay. Now, we don't work with Riemann sums. We use the fundamental theorem of calculus. So all we do is we can simplify the integrand first, and then we find the antiderivative, and then we just plug in the endpoints. And because we're calculating area, our units will be units squared. So the video just had to describe the basic idea, which I've just re-described, and it worked through an example. Did anyone have any questions about this early part before I start another sort of more complicated example? No questions. All right, cool.